Okay, so very good morning and welcome to today's class. Let me give you a quick recap of what we discussed yesterday so that we can take it up from there. We have been talking about ER modeling and we have so far seen the basic components of an ER model, entities, sets, relationship sets, and attributes, different types of attributes, and so on. We have also seen how we can depict an ER model using an ER diagram. We have seen a few alternate possible notations. Also, we have seen in our yesterday's class how from a given ER model we can generate the database schema. So that is very important. And after that, we started looking at some of the uh, relatively advanced concepts, including more than binary relationship. So we talked about ternary relationship and the impact of having multiple such arrowheads and what could be the possible interpretations of those and why we may want to have only one edge with which is directed. That means it is one on that side. Then we talked about this specialization. Okay, so in specialization, we talked about this top-down design process, and we took up this example where we said that there is an entity set, say a person, which has got certain attributes, including a key attribute, and then we have some specialization of a person like employee and student, and it can go to any depth of hierarchy, like from employee we can go to instructor and secretary, and at each of such specialization levels we can have some additional attributes. And typically what we would expect is that the top level entity set will have the key attribute in it, and only the additional attributes which are not supposed to be part of the key attribute, because the fact that a person should be individually identifiable means the attribute for that person, which is the key attribute, that should be able to actually distinguish between multiple instances of some of these specializations or any of these specializations like employee, student, or instructor and secretary. Also, we said that they can be disjoint, meaning that no instructor, no employee can be, employee can also be a student, uh, and we took some examples yesterday. And when they are, so that is when they are overlapping, and when they are disjoint, that means this is, for example, instructor and secretary, both of whom are employees, but an instructor would never be a secretary, or a secretary would never be an instructor. So that is what we have seen in terms of modeling. Now we'll see that how such specialization can be converted or translated into schemas, which we have not yet seen. Now, there are a few possible design choices that we have. But before I take this up, I would like to pause and see if there is any question from anybody. Yeah, you are saying something, Jan?
No, sir, sorry, sir. It's
Oh,
unmuted
no,
by
that's
mistake.
perfect. No, 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 no problem. No problem. Yeah, so anybody has any question? Okay, so let us proceed, but you please feel free to stop me at any time and ask your questions, and you can always ask questions at the end of the class or later on also you can send me mails. Okay, so let us get back to this continuing topic of representing specialization in schemas, in database schemas, or what would be the relation schema for each specialization. So there is one design choice where we form a schema for the higher level entity. When I say a schema, we are talking about a relation schema. And then also we form a schema for each lower level entity set. And what we will have, first of all, for the topmost level, what we'll have is that we'll have the schema for person, and it will have these all these attributes of a person, and whichever is the key attribute also becomes the primary key here. So this ID you can consider is underlined. Okay, that means for this table called person, ID field will be, or the ID column will be the primary key. And then we have these other attributes, name, street, and city. For student, now this student, which is a specialization of person, of course, each student will be a person. So each student also will have an ID, and there will be one row in this person table for these students also, and similarly for the employees and so on. So then what we do is that we have this ID and total credit in a student table, and then similarly we can have employee with ID and salary. Okay, and so that is something we can do. And then again, for the instructors, we can possibly think of another one called instructor table, which will have ID and rank, and another table called secretary, which will have ID and hours per week. So it is showing only for the first level, the highest level, and the next level. So exactly something similar we could also do for these other two, these two entities. We could also have two more tables. So total for each of these five entities, we could have one table each. Okay. So if we look at this, it is a good thing that we are doing. So for the highest level, we get this information in one place, and for the more detailed level, the specializations we can get from the subsequent tables. But one drawback is that if I want to get complete information about an employee, okay, so if I want to get a complete information about this employee, then I have to get part of the information from person, so ID, name, street, city from person, and the remaining part, of course, ID also will be here, but typically you will also need IDs with salary also, of course. But in order to get other details like name, street, city, etc., I have to get it from person. So basically, I have to join these two tables, and then so these two tables means rather I would say person and employee table on the ID column, so that we get name, street, city, and ID from name, street, and city from person table, and salary from the employee table, and ID I can get from either of these. So that is what it means, that this is a possible drawback. An employee requires accessing two relations, the one corresponding to the low level schema and the one corresponding to the higher levels. Now, if we consider method 2, okay, so what we do is that form a schema for each entity set with all local and inherited attributes. So again, we are focusing on the first two levels. Okay, so what we could do is that instead of having that person table, we could have this student ID, name, street, city, total credits. We can have a table at the lowest level. Assume that this is the lowest level. For the timing, let us not worry about instructor and secretary. So we could have one table for employee and one for student, but nothing for person. Okay. So in that employee table, we'll have all the attributes which is special for that student, which is total credit, and then all the attributes which were there in the uh, in the in the highest level. Okay, and similarly for employee, this salary. So as you can see that in this case, uh, all the details about student we get from this table, and all the details about employee we get from this table. So I don't need to join, like in this case, the student to person, to get some of the attributes from person and some of the attributes from student, and similarly for employee. So that is good. But one point that you note is that in this case, because this is overlapping and some students are employees and some employees are students, then in this method, what will happen? Those people say ID1 is both a student and also an employee. Then for that student one, I will have one row here which will have the name, street, and city in the student table, and also for the same ID1, that name, street, and city, I'll have in the employee table. The additional information I'll have is the salary and the total credits. Okay. So that is a drawback. Is there anything else that you notice that what could be other issues, or what could be other possible design choices besides these two? And also you can now assume that we have all these five entities, okay, all the way up to instructor and secretary. So is there any other possible design choice? Or
Single
there are,
table with single table with nullable columns.
very good, excellent, excellent. That is a very good suggestion. So we could have one table, and we could just call it as person, okay, and then there we could have all these columns, these four, this one, this one, this one, this one, okay, and then whichever is relevant for whom, so the value would be put there. Okay, so that way this disadvantage that is being mentioned when we have overlapping such specializations, so that will not be there, as we can very well understand, because for those students, those who are also employees, so for them, for the column total credit, the value would be there, and for the value in terms of for his student role, that value will be there, and for salary, that will be there. Now, of course, for the other ones, what we'll have is that we'll have either total credit or salary, and likewise, if you also have this rank and hours per week also in that same one table, then depending on whether that employee is an instructor, the rank like professor, associate professor, etc., would be written. And if that person is a secretary, then the hours per week would be written. So yeah, so that is a very good alternative possibility where we'll have everything together in one table. Okay. Now, is there any other disadvantage of this design if we want to see, other than these drawbacks? So what will happen is that if we want to get the list of say all persons, okay, in this case, or when we had this instructor and secretary, and if we kept another table called say, instead of keeping this employee table, because employee again can be specialized into instructor and secretary, effectively what we'll do is that instead of keeping this employee table, we'll keep an instructor table and a secretary table, because student does not have any further specialization, the student table is fine. So instead of employee, just as we are not keeping person, we will not keep employee table also, we'll keep an instructor table and a secretary table. And instructor table will have ID, name, street, city, salary, and rank. And the secretary table will have ID, name, street, city, salary, and hours per week. So in that case, actually, for considering all those five entities, we'll end up having these three tables. So which will have one for student, one for secretary, one for instructor. But the disadvantage is that if we want to see who are all these employees of this university, for example, then I have to get some of these data retrieved from like a subset of the data will be there in the instructor table, and a subset will be there in the secretary table. Just as in this case, if I want to just if I forget about that next level of secretary and instructor, so for student and employee, so if you want to get all the people in this university who are associated with the university, that includes students and employee, So I have to get all these people from student. I have to get all the list from employee, and also we have to ensure that we take a union. And in the process of union, actually the duplicates are to be eliminated. So this is what we have to keep in mind. Or uh, so the one drawback is this. The other drawback, of course, is to get to the entire list. I have to get it from the two tables. So while we have reduced a join in this sense, but in order to get the list of every person, we'll have to get this from the student table and from the employee table and do their union. So that is what we need to keep in mind. So if we just want to see how many people are there in this university who are receiving salary, student table and union all those in the employee table and take a count of that. So we have to keep in mind that based on whatever we are designing, there would be those issues. And the suggestion that was given, if we had one table which will have all these, so that will end up, as you will understand, is that there will be a lot of these null column or the other. As you see for this example, for all those who are both students and employees, they will have values for total credits and salary. But a majority of them will be, say, students or employees. And so for all the students, the salary component, the salary column will be null. And for all the employees, the total credits will be null. Now, what we are trying to uh, make a point about is that uh, if it is null, you see the difficulty is that if for an employee, say there will be one table itself which will have ID, name, street, city, salary, total credit. Okay, and let us call that as person. Now, if the salary column is null, you do not know whether this is an employee for whom the salary is not yet decided or this person is a student, because even if the total credit part is null, then also you do not really know whether it is a student, but and the total credit is not yet known, or it is an employee. And if you want to have additional reasoning, that is that, oh, if this total credit is null but the salary is there, then we know that this is an employee. And if this is not there, and then it is a student. And if both are there, then it is a student who is also an employee, or an employee who is also a student. And if none of these are there, then you really do not know whether it is a student whose total credit is not yet decided, or it is an employee whose total credit is decided. So this is the programming logic which is especially if you put everything together and make these null allowed columns, then the someone else who looks at this design will not really understand why all of them have been kept together in a table, and then these have been made null allowed. Is it that because people might join when the salary is not known, that's why it is null allowed? Or it is basically the fact that you are trying to represent two different types of persons in the same, that's why it's kept null. So it may become a little and not I think I dropped off for a second or so, so let me repeat that. So yeah, I think you can see my screen. So what I meant is that there are these two methods mentioned here, and the third method that was suggested by you. And okay, and there is nothing right or wrong about it. It is about a design choice that one needs to keep in mind. And just as, of course, the opposite of specialization is generalization. So it's a bottom we are still mentioning that is that because it is a process that we follow, and we can look at the system like at the top level and then break it up into the lower level. So often the terms the specialization and generalization are used interchangeably. Of course, I mean, if it is a the lower level is a specialization, the higher level is a generalization. In that sense, it is used interchangeably. Of course, the lower level will never be called generalization, or the higher level will never be called a specialization. So that is what I have mentioned. So it can also, as we said, that when we have some of them are having overlapping, that student and employee, then this point will come. That's there could be some redundant rows in these two tables. But if they are disjoint, of course, like this here. But if this uh, specialization is not total, so then what will happen? There would be some persons who are neither student nor employee, then they will not get reflected anywhere. Okay. So in that case, of course, you cannot have this design. You can have this design, or you could have the design where you have one table and you have put everybody in that. Okay. So it is only not only the question of this whether it is overlapping or disjoint, but total and partial, that will also have an impact. So as you can well see that if it is partial, means not every person is either student or employee. There are persons who are neither student nor employee. Then of course this design will not work, because you will not know any information about those people. Okay, so that is what it is talking about, that total entity must belong to one of these, and partial we have already said. The default is partial generalization, meaning that some of them need not be they are in either of the specializations. And in the ER diagram, you represent it by adding the keyword total in the diagram and drawing a dashed line from the keyword to the corresponding. So for a student, again, you can have like graduate and undergraduate students. So by graduate, it means the postgraduate and research students in our institute. So that would be total, meaning that all of them will be either this or that. Okay. Now, just before I take up this one, just remember that here we had shown this total and partial participation, but when now what we are talking about is this generalization. So this for the generalization, of course, as is mentioned here, that when you try to draw this, so you write this total. That partial is default, total in the diagram, and drawing a dashed line from the keyword to the corresponding arrowhead. So if we let us assume that this is total, so then what we'll write? We'll write the word total, and then we'll have this line connecting this to this arrowhead. So that is how we'll represent total. And by default, it is partial. Okay. So that is what it means here. Okay. Is there any question up to this? Okay. So if there is no question, so let me take up this part. Uh, that there are certain things that we have to keep in mind, and sometimes we make those. Uh, I would not say mistakes, but maybe that is not a good way of modeling data. And if it is not really good, I mean, if it's not good at all, it is like a mistake we can consider. Is these design issues? That is, let us take this example that sometimes we are not very sure when, and you might have also faced something similar in during the first lab that you did last week, that whether you will put something, name something as an entity, or will model something as an entity, or you would model that as attributes of another entity. Okay. So let us see this, that I have, say, this phone number. Okay. So these are two alternative ones. So this phone number attribute, or this phone number, this component, will it be an attribute of instructor, or it will be an entity on its own, and then having a relationship connecting instructor to phone number. Okay. So what it uh, means is that when that component, say phone number, it is not having anything other information associated with it, then we'll typically put it as an attribute. So like phone number we are putting here. But if that phone number has got something more associated with it, as if that there could be certain other attributes associated with it, then we will model that as an entity set. So if you see the second example, we have phone, and then we have a phone number, maybe the location or so, whatever it is, the location mean in which building that phone number is located, so you can trace if it is a landline for that matter. Okay. Then you will be putting that as a separate entity. Of course, or for example, if we consider mobile phone, so if you want to put phone number and then which is the service provider, and suppose we need to keep what plan is currently active and so on, in that case you may want to model that phone as an entity of its own. Okay. So as you can see, we are saying that use of phone as an entity allows extra information about phone numbers. And what it shows here is that what type of relationship is it between instructor and phone? Is it one to many to many, one to one? What do you think?
Many to many.
Yeah, perfect. So this is many to many. So because it is many to many, so when you will be getting the schema out of it, you will have an inst phone as a separate table where you will have ID and phone number as its two columns, and ID and phone number together forming the primary key. And then you can keep for one instructor multiple phone numbers. Of course, what you could also do is that if it was one to many with that table out of phone number, you could also keep the ID. But by keeping it many to many, for example, so this is not exactly true. Use of phone as an entity allows extra information about the phone numbers. That part is correct. But multiple phone numbers I could do if there was no extra information to be kept. So I could have made this phone number as a multi-valued attribute also. Okay. And then, as you know, that for that we'll have a separate table called instructor phone with ID and phone number together forming the primary. So, so these are possible design choices which you may have to handle. Now, whether something will be part of entity or part of relationship, so what it means is that so uh, so what we do is that, say, if we have, say, a student and course, let us assume this. So this is one example, but I'll give you another simple example. So if we have student and course, and we say student registers for a course, so student is an entity which has got these attributes, roll number, name, etc., and course is an entity which has got attributes like course ID, number of credits, course name, and so on. So suppose I take that example, student and course, and we have this relationship registration which connects the student entity to the course entity. So if we do that, what would be the cardinality of that, you feel? Anyone? Student to course, is it one to many or many to many or one to one? By
Many
course
to
I
many.
mean the subject. Yeah, perfect. So subjects, yeah. So one student can take multiple courses, and one course can be registered by multiple students. Very good. So it will be many to many, right? Now it is similar example. It is saying that whether the student to section, we will have and again, let us assume for the time being that this section as it is showing is a strong entity for the time being, because within a year and semester and section ID that is unique, or it might have been a weak entity of a course strong entity, but that is immaterial. What is being talked about is that in this case, whether and in our example also between course and student, whether we'll call registration as an entity set or registration as a relationship set. So if we model it registration, if we might feel that, oh, registration is important, something I model it as an entity set, then we'll have from student to registration as one relationship, and registration to course as another relationship. So you see that that is what it is also talking about between registration and section and registration and student. But this possibly you see is not so intuitive. So what is important is that we have to follow some of our intuition that what exactly is happening is that registration, an entity should have its own existence, but it is more like when a student is registering for a course, then only this registration is happening. So in that case, it becomes more like a better choice is to make the registration as a relationship. And placement of relationship attributes, whether the attributes you will you remember we said that the relationships can have attributes, whether those attributes will be associated with the relationship or it will be associated with the entities that that relationship is connecting. So in that also is something that you have to consider. So that is why we are talking about these as design issues. So if you remember very first example, I'm just going back once for your convenience so that you can relate what we are talking about all through in this particular topic. So if you look at this example, so instructor to student, and this tells us the date when that student was associated with the instructor. So as you see, obviously that this is this date is going to be an attribute of the relationship. It does not belong to student, does not belong to the instructor. Okay. So, but you see that if it is one to one, you could possibly think that I could as well make it an attribute of the student, because it will be unique for a student for the instructor, because the instructor to student is one to one anyway. But that is what we are talking about as this possibility placement of relationship attributes. But as you can see that attribute is coming into picture because of the relationship, not it is an inherent property of a student or an inherent property of the instructor. So it would be good to place it with the relationship. So this is also another design issue that often we keep in mind. Binary versus non-binary, as we have seen that for ternary relationship, it is usually mm, a little complex, and you have to ensure that you have appropriate cardinality defined and all. So it is possible to replace non-binary relationship by a number of distinct binary relationship sets. But sometimes an n-ary, say a ternary or so relationship set shows more clearly that several entities participate in a single relationship. So if you want to model it like that, so initially you can have a ternary relationship to show, and then you can again blow that up and say that, oh, this I am dividing into multiple binary relationship. Okay. So a ternary relationship, parents relating a child to his or father and mother, is best replaced by two binary relationships, father and mother. So for a child, you could break up a ternary relationship to two binary relationships. But some are naturally non-binary. Again, if you remember, we said that ternary relationships, like this example, the instructor, project, and student. So this, of course, this project guide is this instructor is not guide for the student for every project. Okay. So this is instructor is guide for the student for a particular project. So this is a more natural situation where you would like to represent or model this type of relationship as a ternary relationship. So that is what we are saying here, that we may have to have certain situations where which are inherently and naturally non-binary, and it would make sense to appropriately model those. And of course, if it is non-binary, so if it is ternary, so as is shown here, so it is possible to replace this by this type of binary relationship. It's fairly easy that if we have this R, A, B, and C, what you do is that you simply break up into three such relationship sets. This R, you break it up into this E and E you add as a separate entity, and then what you do is that this R, that relationship, the A's participation in the relationship, you make A participate in a relationship RA with that E, which is an entity set which you have come up with replacing this ternary relationship. Similarly, this B's part, B's participation in this relationship, you replace it with B's participation in a relationship RB with E, and likewise C's participation in this relationship you replace with this RC with E. Okay, so replace R between entity sets A, B, and C by an entity set E. So this R itself you are replacing by um, this one, by those particular relationship. Is it clear? So basically, what you do is that create an identifying attribute for E and add any attributes of R that you possibly had. Like if you had a date attribute for that project, instructor student relationship, so those will add as attributes of E here, and then you simply have this these relationships replaced by this between A and E as RA, B and E by RB, and C and E by RC. So that is what we will do for converting any non-binary relationship to binary form. So naturally, actually, we'll see that most of the cases you will have these binary relationships. And ER design decision, so use of an attribute or entity set to represent an object. So that is what is important. Whether a real world concept is best expressed by an entity set or a relationship set, you have to keep that in mind. As I said, that student to course registration. So registration is a real world concept. So whether registration should be an entity set or as a relationship set. The use of ternary relationship versus a pair of binary relationships, that is what I discussed. Strong or weak entity set, of course, we have said that if that entity set, like as I said, that if it is a children of employees that we want to model, then we have to model that as a weak entity set. We cannot force any key attribute for that. Rather, we'll have those discriminators. And specialization, generalization, of course, that helps in modularity of the design. So instead of coming up with different, completely unrelated entity sets, we would like to show them in the form of specialization and generalization. So these are the, of course, what we have already discussed before, the summary of symbols, what these are, and the symbols that are used in notation. So these are, so this is this example that if this dotted line and total, if you remember, we said that disjoint generalization, and partial is the default, okay, and the other alternative ER notations also already we have talked about. So that brings us to the end of this chapter 7. And once again, please take a look at the book, go through the details of this chapter. And now what we'll do is that, so if there is any question, please feel free to ask.
So,
Yeah.
so like in today's class and in yesterday's class, sir, you said that to find an entity's details in two tables, we need to join them.
Right, right.
But sir, why can't we like search on both tables? Like, let's say in one table we can get a primary key of the second table, and we can search in constant time. Why is there a need to join?
What is meant by searching in constant time?
Like, let's say we have a name and we need the salary of that person. So in one table we can get the ID, and we can search for the ID in the other table, and get the salary.
Right, very good question. So first thing is that so from that name getting the ID, it is not necessarily first of all in constant time. Okay, because for that name you have to figure out, because in the table what you are looking at it you see, but it is when it is stored in the database, your query processor will have to first identify where that particular row is located for that name. Okay, so as we'll study later that there are ways of doing indexing to speed up, but otherwise you can assume that these are stored in an unsorted array. I mean, it is physically not going to be stored in an array. So if we do not store it in a particular order, so in the worst case, actually you have to search through the entire table and it will take order of n, right?
Yeah, okay.
Okay. Now, once you got the ID, again you search the other table. That also again you have to do it in order of n,
And
right? Because
yeah,
okay, but so that is one aspect of it. Okay, but what is more important, I will tell you. What you are saying is that I search in this and then I search in this. Okay, so it is not something that ID you will get. You can store it in a variable and then search and so on, because then you are talking about writing this SQL embedded in a high level programming language. Okay, so if you are only using SQL, then what you are saying is partially correct, meaning that uh, uh, it will use what is called a subquery. Okay, so there is something like a subquery where ID in something, etc. So this writing an SQL query using join or subquery, these are two alternative ways of writing things. Okay, so what you are saying is a way of querying it using subquery. So you will try to figure out salary and other details from one table where that ID is equal to, say, select ID from that first table where name is equal to the
name is
given.
equal to something.
Right. So that is a subquery. Now what happens is that when you have many such things, many such tables from which you have to pick up pieces of data, in that case writing subquery will become more complex. Okay, I mean it will read more complicated, and writing it as joins is much more straightforward. And sometimes, so whether you are actually using joins or subquery, the database access time will be heavily affected. So when I said that joins we have to avoid, means also subqueries are to be avoided. That's the baseline. Okay. So what I meant is that searching for data from multiple tables is always going to be costly than searching it from a like less number of tables. But it is not to say that for reducing that query execution time I'll mess up with my database design. So that is not done. Okay, so that's why we have to ensure that we have a correct design so that my database that we design is in line with the data model, and at the same time unnecessarily we are not keeping data in redundant tables, which will result in additional query execution time. And that I said, as you have pointed out very correctly, that join is always expensive, but join and the subqueries are something very similar. These are two different ways of representing similar query requirement, but writing using joins usually looks much more neat. Okay.
Yeah.
Okay. But very good question. Any other question? Okay. So if there is no other question, so I am stopping the sharing, but the recording will continue. Now we'll pick up topics from chapter number 2, and that will be covered by Professor Ghosh. So Professor Ghosh is here, and he will take over. Professor Ghosh, so would you like to now?
Right. That will
Okay.
be great.
Okay. So I am muting myself, but the recording is continuing.
Okay.
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 Thanks.
Thank you. Let me share the thing. Hello. Hope you can see the PPT, right?
Yes, sir.
Yeah, that's good. So good morning, and so I will continue this one from Professor Sural, as you have already had a overview of the database design aspects and specifically on the ER model. So we'll go now go towards this relational model and gradually looking at the SQL. But as mentioned in the class also in previously during the introduction and the lab, so SQL you need to practice. It's a something which you need to work at your home, and also you may be doing in the will be doing in the lab. So let us start. So what we have seen so far, or what we understand when we look go for a database design. So what is the why we are doing? We are trying to have a say a real life situation to be modeled in such a way so that I can have a better way of say managing data. In the term managing means we can basically insert, update, query, delete, and reorganize if required. Right? So this is our basic motto of any physical any real life situation. Let it be our ERP system, or let it be our academic dynamics, which we want to put it on a ERP system. Let it be a library dynamics, we want to put it on a library system, and things like that. For that, first of all, what we need to have some sort of a logical modeling of the whole thing, right? A model what you create in terms of what you did in ER model, or later on there are other way of means modeling also. You might have done that UML and things like that. So what we are trying to do, we want to map that real life situation into some sort of a now when we want to work on on now the systems where the query language will be there. There are issues of say transaction management, concurrency control, or say even normalization, where we want to reduce redundancy and things like that. So for those, I require some sort of a more specific model which is tuned to my this sort of handling this SQL and other type of. So one such very predominant model these days, or for say for say in practice, is the relational model. So what we do in case of a relational model, uh, so the it consists of, so what if you look at our if your ER diagram, where you have entities and their relations between the things, right? So an entities, every entity are having different attributes, may or may not have more than one attribute. Relation may also have attributes. Right? Now, when I want to make it more generally means represent in the system, so what I need to do, I need to have some sort of a representation so that I can easily query on. So one such thing is this, or what will be this, what the whole course is all about, is that relational database model, right? So we'll be working mostly on relational database model. If time permits, later on we'll see other type of things which are extension of this. So what it says that a any such entity relation with their attributes can be represented in a two-dimensional tabular form, where every row or every tuple in database term is basically talks about a relation among that set, right? So like here, if we see that every row, so it has some ID, a name of that person, which department he or she belongs, and a salary, maybe in a monthly or annual salary, something it is representing. So every row is represent a something, a related item set, right? So these are the things which are related to this person called Srinivasan. It may be with a person called you, Mozart and Einstein and things like that, right? So and and this collection of uh, such tuples, what we call as a table. Right. So this a very nice and simple way of representation of what you map as a logical model to basically to a model where we can basically query on the things in a much easier way. Right. So now my entity along with attributes can be represented as a relation. My in the entity relationship diagram, my this relation where that so-called that relation in the ER model can be represented by this sort of a tabular form, right? So now if I have my a database stuff with all these relations, then I can basically query by this combining, or as you are as Professor Sural was discussing in the at the end of the thing where when I joined that finding say joining two tables, joining more than two tables and querying and giving different type of predicates and do that, right? So so if we see this about this attribute type, so every row of this or every tuple has a set of attributes, right? Like name, department, salary, things like that. And this ID in this case is an identifier. We'll come to that. Right? So rather, it also consists at the one of the attribute type of this particular relation. If I say this is a relation of employee, the relation name R is of employee, which has a employee ID, employee name, employee department name, and employee salary. It can be a lot of other attributes as well, right? So, so what we say, what we see that this each attribute has a set of values which is allowed in that attribute, which we call it as domain. Right? Like if I say in this case, like department can have the department which is say, if I say IIT Kharagpur, so the department name should be one of the department which are existing in the IIT Kharagpur. In this institute, right? So that is the domain of this particular attribute. Similarly, I can have a salary name, some construct for that, right? So the domain is for every attribute has a domain or set of allowed value in that domain. Right? So attribute values are required to be normally atomic, right? So that means they are non-divisible, right? So why we are calling normally, later on we'll see that there may be a non-atomic type of things. Like in this, suppose I having another attribute called phone number, and the phone number, first of all, one particular employee may have more than one phone, right? So, or even if there is a single phone number, the phone number may be divided into country code, area code, and the number itself, right? And the number itself. So that way we can think about non-atomic. But as of now, whatever we are discussing, considering this relation to be this domain to be atomic, or attribute values are atomic, right? So, and there is a special case of value which is null, which is, that means it indicates the value is unknown, right? Here if I have, say, as I was telling, there is a phone number and one employee do not have a phone number, then the value of that particular attribute or for a particular tuple will be null, right? Or if the department is not assigned to something for when initially joined, it may be a null or something else, right? A phone number may be a good example to that. So the null values causes complication in defining, in many operations. So So we do not encourage keeping null in the thing. So that means, so this any type of unknown things, well, you'll see when it is query is coming, then we'll see that in this type of creating, having null value in the domain, always create a problem into the system. Right? So that is the thing, but nevertheless, this null is a domain may have a null value. So what we see, so there are, if there are attributes say A1, A2, AN, so I say the relation is considered to be R. A relation R is A1, A2, AN, and dot dot AN. Like in this case, what is there? Relation is ID, name, department name, and salary. Right. So this is my the relation is instructor, as I was telling employee. Maybe the this, let us consider relation name to be instructor, which is having this are the consists of this attribute set, and we define it as that as a schema, right? So when we define a when we define a database, or so it may have this sort of relational schemas, right? I say that my IIT Kharagpur academic database has a schema called say instructor. There can be a schema called student, which is having again ID, which represents student ID, student name, maybe department where he or she belongs to, and maybe some other things like which program is enrolled, right? It can be BTech, Dual, MTech, PhD, MS, and things like that, right? So there can be different type of attributes. So this schema is important because it defines that what will be the construct of my that particular table. So what we say, this is the schema, and every tuple or every row in the table is a instance of that particular schema. Right? It should conform to the things. And once we define the schema in this fashion, then all this domain etc. For the different attributes are also defined. Right? So formally now we can say that if these D1, D2, D3 dot dot Dn a relation R is a subset of this cross product, right? So if these are the domains, right? So given set these are the things, so it is a subset of this cross product. A relation R is a set of n tuples, and A1, A2 tuples, A1, A2, An, where AI belongs to this particular Di, right? So this I can formally define. So so any value or relation instance of a relation is specified by a table. So I get a thing which is specified by a table. And a element any element T of that particular relation R is a tuple, represent a row of the table, or what we say tuple of that particular relation. So the beauty of this relational representation is that everything we can we represent as this two-dimensional relation. So I say that your entity is a relation, your that in a ER diagram the relation I can mapped as a relation. So everything is represented by this sort of a table. So that is more simple and more generic representation of your whole database things, right? Now, how many tables will be there in in your particular while developing a particular database for a particular say application? That depends on how your database things are designed, right? So how so there are a lot of aspects of designing will come slowly into the things, and your good way of designing will help you in efficient query processing, right? So so what we see that given a relation, in this case instructor, we have set of rows or tuples, and as we'll see, as it represent it conform to the set theoretic approach, so no two tuples are repeated, right? So all tuples in this particular table in a relations are unique. That means there is no repetition of the, there cannot be any duplicate tuple into the in a particular table. So another important thing or another things to be noted is relations are unordered. So order of the tuple is irrelevant. Right? So tuples may be ordered in any arbitrary order, so that it does not restricts in that what way things to be ordered. Right? Later on, we'll see some of the things when we'll look into that how do I store. So what we are having now, as of now, we are not looking into that how physically things to be stored, right? How physically things to be stored. If I want to search something, how it will be searched into the things. Those are we are not. We'll see later on. So, but as of now, what we see these relations as of these tables does not have any constant of that this need to be ordered. Right? It may be, if it is ordered, it may be easier to search, etc. That later on it. So typically that instructor relation is unordered tuple. So as if as and when the data is coming, it is pushed into this particular relation. There is another important thing which we see, that if it is a set of tables, so how uniquely I identify this every tuple. So if this set of instructor, so one way of looking at it is that to as we say there is no repetition, so I can have the whole tuple as that identification. So that ID, name, department name and salary, I say that all together makes a unique thing, absolutely, right? Because there is no repetition on that in any of the tuple. Or now that may not be a elegant way. You may say that the ID is also not repeated, ID may be there, ID name can be there, right? So that what we see, that what are the keys or the by which I can identify the thing. So so key K is a, what we say is a subset of this relational schema, that what are the attributes set in that R. So K is a super key of R if values of K are sufficient to identify a unique tuple of each possible relation R in R. Right. So in this case, ID is a super key because it can identify the relation in a unique way, and anything, any superset of this ID is also a super key, right? That also uniquely identifies. Say ID name is a super key, right? So rather ID name, sorry, ID name, department name, these are all, this is also a super key. So I can have different set of super key. So I say a super key is a minimal, right? Again, coming from our basic knowledge of this set theory. So that if it is not divisible, right? So if I say that ID and name may not be the minimal thing, right? So a super key is a candidate key if the k is minimal. So I say those super keys which are that cannot be divisible, so that it lose that identity of uniquely, lose that property of uniquely identifying the things. Those are candidate keys. Right? So here in this case, particular thing, I may say that the name is not repeated, at least considering this tuple. So name can be a candidate key, right? And ID is a candidate key and things like that, right? So there can be different candidate key. If there is a phone number, if it is unique phone number for all employees, usually, then we can have that those as this candidate key, right? If name is repeated, but if there are no two name of the same person, which is not a good assumption, name in the same department. So name to department combination can be a candidate key, right? So I can have different candidate keys. So out of this candidate key, one key is selected as the primary key of the thing, right? So in these candidate keys are all candidates for to become a primary key, and whereas that primary key is one of the keys selected. So which one you select, that also that depends on that which primarily it depends on the decision of the database designer, right? And based on the type of application he or she is looking at, right? So considering the other tables and things, right? So any of this candidate key can be selected as a one as the primary key. So in this case, the natural choice can be the ID, right? This ID, say employee ID, are not repeated. In the student case, the student ID can be the candidate key. Right? So there is another thing which is what we called as a foreign key. Right? So like a relation R1 may include among its attributes the primary key of another relation R2. Right? Like I can have here instead of department name, which are unique, maybe we consider as a unique, right, or department ID. So that may be a primary key of a department table, right? So in this case, R may include among the attribute of a primary key of another relation R2. This attribute is called foreign key of R1, referencing R2. Okay, so it is a foreign key from R1 which is referencing R2. The relation R1 is also called the referencing relation of the foreign key dependency, and R2 is also called the reference relation of the foreign key reference relation of the foreign key. Okay, so this is this type of constant. So value of one relation must appear in the other relation. Right? So one is the referencing relation and reference relations. So the department name in the instructor, as we are telling, is a foreign key from instructor referencing the department relation or the department table. So three type of so primarily what we have seen, that one is super key, which is uniquely identify that each possible relation in R, like ID name, department name, anything that all those things. And there is a candidate key that where those super key which is where the k is minimal, super key k where the k is minimal. And out of this candidate key, one is selected by the database designer as a primary key, right, for identifying that particular relation. And we have a concept of foreign key where value of one relation must appear in the another, right. So in this case, the department name in the instructor relation is a foreign key to the instructor referencing to the department. Okay, so we'll see that how this where it helps and how things we can use those keys. So this is a ER diagram. So these are different department, instructor, and different relations are there, like instruct, department, advisor. Instructor can be advisor of student, right? And so student, this department to student relations, and there are so these are the entities: department, course, section, classroom, time slot, student. These are the entities, and these are the relationship between the things, right? And some of the relations in this case, like that a this some of the relations are having attributes of that particular relations. So this, if we try to represent this in a schema form, right? Database schema. So we have a student schema where ID, name, department name, total credit things are there, where it is coming from the student schema. Right? Where if you see, it has a foreign key as a department name, which is a primary key of the department, because students belongs to a department, right? So we have a other schemas like say instructor. So say instructor is ID, name, department name, and salary. So again here this ID, name, and salary are the attribute of this particular instructor, and the department name is a foreign key from the department. So what we are trying to do from this ER model, we are now coming to this representation of a schema model, right? Now, other thing is that this individual relations, as this relational model in this individual relation have this schema which takes care of this, not only this uh, they are attribute set, also this referential constant, right, or this foreign key constant, right? So I can basically boil down to a from this ER diagram. We can now represent it and as a set of tables or relations which basically represents this ER model. Right. Now I can work with this only these schemas which are student. In this case, this text is what is that? Text is a relation. Similarly, here we see that teaches is a relation, right? In the ER model, which is represented now by a table. So that is the way that exactly what we were started with. Now I can map this whole this ER diagram by which you have basically modeled this as sort of a real life scenario, a scenario into a some sort of a conceptualized it. Now we can have a some model this relational schemas for those models. Now, if I now represent them these things in some form of a in a database, then I can query on these considering these tables. Right? That is our goal of what we are going when we are going for the SQL things, right? So I can basically it represents these schemas, and I can populate these tables, and now based on the data available, and then I can query on this table and find out different sort of informations based on my need of the query. So when we look at relational query languages, so that is there are procedural versus non-procedural or declarative languages. This is as far as the query language is concerned. So there are what we say quote unquote pure languages. One is relational algebra, tuple relational calculus, and domain relational calculus. We'll see relational algebra now, and we'll look at to other things when we in maybe in the subsequent classes, right? The tuple relational calculus and domain relational calculus. So this today we'll try to see that how this basic construct of the relational algebra and how it helps in resolving queries, what we'll be looking at when we look at the SQL things. So some of the basic operations, one mostly used operation is the select operation. So what it says is select of a set of rows or tuples from a relation based on some based on your some attributes, based on some condition, right? So in this case, what we are looking at, say if I have a relation R and then apply this select operation, we end up in another relation R. Or in other sense, if I have a relational table with the data set and I apply any operations, we end up in another table. So input is also a one or more tables, and output it generates is a table, right? So whether in any, for that matter, any SQL operations will end up in another generating a another new relation. Right? So in this case, what we have that select A equal to B or D greater than 5. Right? So this is my condition. So if I have A, B, C, D 4 So my relation R schema is A comma B comma C comma D, and I have other data sets like these are the different instance of that things or different tuples. And if I have select some condition on relation R, so it end up in another table. So it is, this is the that in this case, if A equal to I am selecting where A equal to B and D greater than 5, so I end up in this particular thing. So this is a select query where a subset of these tuples or rows are generated as the output based on the based on this condition. So if this is a single table, if there are more than one table, then we'll have some join and then select those tuples which satisfy that. So that is another operations which is project. So what we see here, if we are working on one relation, considering a relation R, so in select, the attribute set remain same of the input thing and the output table, whereas the number of that tuples changes into the things if the selection is in that fashion. Suppose if the selection is if A say select where D is greater than 5 or greater than 1 on R, then I generate the same thing in particular in this case, right? So all D this with the particular this your condition, all tuples are selected. But it generally says it keeps that whole attribute set in the output generated tables. In case of a project, so what we see, it is basically select a set of attribute or set of columns. Right? So if I have a project of A and C, right, then what it is projecting? It is projecting A and C. Right? So in this case, it projects alpha 1, beta 1, beta 2, right? As alpha 1 and alpha 2 are repeated, so it end up in that only one instant of the thing. Right? So what we see here, once we project, whether on a single relation or after doing some joining, then I end up with a subset of this column. Right? So original attribute set, and this I have this attribute set only. Original was ABC, attribute set in this case is AC. Say that may be sometimes required that you want to do some operations with a say student relation along with a department and relation, and you want to shortlist or list only those roll number and the students and say roll number and their hall who belongs to something like CS department, right? But I want to list only the name, roll number and the hall name, right, of that particular student. So I basically do a maybe a join with the that hall table or HMC database, HMC schema or hall schema, and so then do a project to project out only the roll number, name, and the that name of the hall. Okay. So these are the project operations. So there are other set theoric operation like one is union. So when we union R with A's, in this case R is AB this set and A's is this one. So what we do basically a we generate this union set, right? The only constant is that here that your tuples are not repeated, right? So if you have like alpha 2 appearing both the sets, so it is one instance is repeated. Okay, so what we require that this Rn is of the have the same attribute set, and then we do a union on that. Similarly, when we do intersect subtraction or A minus B, so as we know that only those tuples will be there which are present in R but not in S, right? Which are in R, not in S. So as again, it is following that the concept of relation what you have read earlier in your other subjects, and that concept of set theory. So intersection, same way, we it should be that like R minus S, right? So it is intersection between the two relation A, R and S. So this is the relation when we do that intersection operation. So what we try to see here that all these operations are possible using what we are looking at is the construct of the relational algebra, and which basically we'll see that all these constructs are available when we look into the SQL or we do SQL queries, right? So all these things, if it is represented in this relational algebra, um, this relational algebraic domain, then those are basically I can do a SQL queries on that. Now we come to that Cartesian product, again following the same philosophy. So AB and CDE. So the Cartesian product of the whole thing will end up in this sort of relation. So it is basically R cross S which is being constructed out here. Right? So I can have joining two relations using a Cartesian product. Right? I can have other thing, like in this case what was there, it was that AB to attribute set of R and attribute set of S are non-overlapping, but there is no common attribute set between the things. If there is a common attribute set between the relation R and S, then we can basically look it in some sort of a, there is a naming issue, right? So what we do, R dot B and S dot B. So we represent this in this sort of a fashion when we go and do a cross product. Okay. So if these two tables are there, then we represent them in this sort of a form. There is a construct for renaming a table which says that this row XE, that means allow us to refer a relation S by more than one name. Right? E under the name X, right? So what we see, relation R, and rename this R as S, and then if we do a Cartesian product, so it is some sort of a what we are doing R cross R, but renaming it as a S. So we have R dot A, R dot B, S dot A, S dot B are the four attributes of the resulting relation or resulting table. Okay. So when we look at the composition operation, right? So as of now, what we are trying to do is basically given to relation, we want to do that Cartesian product. If there are naming conflict, then we use this that relation name dot that particular attribute. If it is some sort of a doing a Cartesian product with the same relation, then we can rename that relation to some other relation and resolve that naming conflict in the attribute set. Now, if we have a composition of operation that can build expression using multiple operations, like I want to do a select with a Cartesian product, right? So I want to do select A equal to C from R cross S. So same, initially the Cartesian products are generated from R cross S, what we got here, and then select those tuples which satisfy that this condition equal to B. Okay, or this particular predicate A is equal to B. Select A equal to B R cross S. Okay. So another concept which this you already Professor already was discussing is that joining two relations by a natural join. Let R and S, if there are two relation R and S with schema R and capital S, right? This is a basically a way of representation, or that when we define the schemas we use these capitals, and when we talk about the relation, those are represented by the in the small letter. So that is a some sort of a de facto standard being followed. So then the natural joint of R and S is a relation on the schema R union S obtained as follows. So consider each pair of tuple TR from R and TS from S. If TR and TS has the same value on each of the attributes, then we do a R intersection S and add that tuple to the R. So T has the same value or as TR on R, T has the same value of TS on S. So that is the way the natural join works, right? So natural join, when we talk about the natural join, so it is what we are trying to do, we are trying to do out here, right? Say we want to project AR. So first of all, you do a R cross S, that is Cartesian product, and select those tuples where R of B and S of B and R of D and S of D are there, and then we project that R of A of A, R of B, C, R of D and E. And as R of D are S of D and R of B are S of B, so we actually project one instant of that. Right? So that the Cartesian project, which will be that is the natural joint, which will be doing which you will be using in the SQL in extensive way. So when we say that that when we do that from say select so and so from relation so and so where this condition, and then what we do, those when we add the from clause, we do a join on those relations. So there are other there are different other options. So each query input is a table that already we discussed. So query input of each query in SQL or any that query language is a table, right? Output is also a table, right? All data in the output table appears in one of the input tables, right? So that means you are not taking any extraneous data from the thing. So it is output is generated using those different operations what we looked into, right? There are other things what we can compute is that sum, average, max, mean. So we'll see that some of the other things like extension of relational algebra when we discussed in later in some of the chapters, right? So what we see here that all this from the ER diagram or any this sort of conceptual model, we can generate a relational tables. We can generate the relational tables following this our relational database model, and all the input entity and relations can be represented as table in a relational model, and whatever the query, it acts on these relational tables or act on these tables and basically generate another another set of table, not set of table. It will basically every query will generate a particular table, right? So the beauty of the whole thing is that only handling these two-dimensional tables, basically we resolve the different set of queries, right? That will see in the thing. So our there can be other type of computation, that is sum, average, max, mean. Those are those can be done, and there are other extension of the relational algebra that we will see once we look at later in this particular lecture, somewhere in the chapter 6 of this particular book, what we are following, we will see. So this is a summary of algebraic operations what we looked into. Like one is the selection, which selects a set of rows or returns a set of rows from the input relation, or this input relations by doing some operations. It returns a set of rows, right? Project is basically returns a set of columns for all rows. So in case of selection, all columns, but a set of tuples. But in case of a project, a set of columns, but all tuples. So output specified attributes from all rows in the input relations, remove the duplicate tuples from the output things. That is obvious, because it follows that set theory concept. And Cartesian product. So output pairs of rows from two input relation that have the same value on all attributes that have the same name, right? Union, that is of that output of the union of the tuples from the two input relations. So I can have like here union, that it projects this from the instructor relation the name, another from the student relation it projects the name, and it makes a union of these two sets, right? So both have one column, right? Set difference, output of the set of different tuples from the two input relations, right? So a given R minus S, so it those tuples which exist in R but not in S, that is. And the natural join, output pairs of the rows from the two input relations R and S, say, or in this case instructor and department, that have same value on all attributes that have the same name, right? So in instructor and department, what are the things we are having common is the department name. So based on the department name, I basically join these two. So when so what we see when we look into the relational query in our subsequent class, that what we will see that we'll be using these basic relational algebra operators in the form that where SQL in the form that how the SQL will be used. So based on the construct of the SQL, and can do different type of queries. And most of our standard databases, as of now, you are using MySQL and Oracle. So all standard databases supports this SQL, right? So what the SQL will be doing, the standard SQL, they will support all that whatever we are talking about in the relational algebra operators. There are some extensions that we'll see while working with the SQL and in the subsequent chapter. But some of the things which are typically not supported by the standard SQL is that your say transitive type of things, like A implies B, B implies C, C implies D, A implies D. So those type of things are not directly supported by this SQL. We need to do some other things to work on those type of things, right? So so like things like that, I want to find a connectivity of traveling different mode of things, like then want to go from here to say somewhere Delhi, and here to with different mode, like so it A to B, B to C, and things like that. But you cannot write a single SQL standard SQL query on the things that we will see later on. But nevertheless, all these relational algebra operators and the relational algebra, what I should say, that concept are being used in while writing this SQL queries. Right. So SQL query will take up in the next class, in the tomorrow's, not tomorrow, next Monday's class. So this is the basic concept about relational algebra and the things of and basic relational model, how it works. So if you have any query on this, we can let me come up to this. Yeah. Yeah. So if you have any query, we can discuss now. And the SQL based on these things we will be starting in the next class. But I believe you have already maybe working on MySQL, etc. But basic construct of SQL we will formally discuss in the class.
So there is this announcement that next Tuesday we'll have the first quiz. So during this class hours itself, there will be a short quiz of about maybe 10 to 15 minutes. And the syllabus for that is whatever has been covered till today, right, Professor Ghosh? That is what our plan was.
Right, that is
That
good.
was the
And it will be
syllabus.
on Moodle, right?
So yeah, so that is important that all of you please also make sure you have enrolled yourselves in the theory component of the course in Moodle. Mm, I believe all of you definitely have done. For the lab, you have done it, but similarly, you also do it for the theory
Theory.
class, so that at that time there will not be any issue.
Right. So next Tuesday will be 8, 20,
25th.
24, 25th, right?
25th.
25th. 25th. Somebody is asking about the this week's
Yeah, so
lab.
for this week's lab, we'll have ER model, database design, and simple SQLs on that. Okay, I think if there is
Okay.
no other
Then,
question, yeah, maybe we'll close here for
uh,
today.
so we're stopping the recording.
Yeah, yeah, please.